Okay, so we're looking at reviewing for the final tomorrow, and we're going over an old exam that I've given on the last material that we had covered from the last exam to now. And so now we're looking at a problem that's going over sequences and series. This problem is just sequences. So this says find the first four terms of a sequence when a sub 1 is equal to 3 and a sub n plus 1 is equal to 2 times the quantity a sub n minus 1. So this is a recursive sequence. This is where terms are in terms of the term before it. So we have a sub 1 is 3. We're already given the first term, and so we want to figure out what a sub 2 is. Actually, let n equal 1. If we plug in 1 in here, this would give us a sub 2, and this would equal 2 all times a sub 1 minus 1. But we're given what a sub 1 is. A sub 1 is 3. So this is equal to 2 all times 3 minus 1. So this is equal to 2 times 2, which is 4. So our second term is 4. If we let n equal 2, we would have a sub 3, n plus 1 here is a sub 3. This is equal to 2 all times a sub 2 minus 1. Well, we just found what a sub 2 is. A sub 2 is 4, so we have 4 minus 1. So this is 2 times 4 minus 1 is 3, so 2 times 3 is 6. One more, let n equal 3. If we let n equal 3, plugging it in, we have a sub 3 plus 1, so a sub 4. This is equal to 2 all times 2 times a sub 3. Oops, an extra 2 in there. 2 times a sub 3 minus 1. Again, we just found the term right before a sub 3, so this is 6 minus 1 inside the parentheses. So 2 times 5 gives us 10. So this is a sub 4. It asks for the first 4 terms of the sequence. We're given the first term, and so we could start listing it. Our first term was 3, our second term is 4, our third term is 6, and our fourth term we found was 10. Okay, so the next question states, write the first 4 terms of a geometric sequence when the first term is -1 and r is 2. Okay, so it told me that this is a geometric sequence. So I know my a sub n term for a geometric sequence, one of the forms is a sub 1 times r raised to the n minus 1 power. We're given what our a sub 1 term is, which is -5. So we have a sub n then is -5 all times r, but we're given r is 2, so 2 raised to the n minus 1 power. So now we can find the first 4 terms because we know the formula for the nth term. So a sub 1, plugging in 1 wherever you saw an n here, is -5 all times 2 to the 1 minus 1 power, 2 to the 0 power. So this is -5 times 1, which is -5. A sub 2, so going back and now plugging in 2, where you see an n in the a sub n formula, we have -5 times 2. That 2 is raised to the 2 minus 1 power to the first power. So this gives us back -10. A sub 3, we would go back in and we would plug in 3 where we see an n in our formula. So we have -5 all times -2, which is raised to the 3 minus 1 power, which is squared. So a sub 3 is equal to -5 times -2 quantity squared is 4. So this is -20. One more, plug in 4 where you see an n, so you have -5. To the negative, or 2. I'm sorry, let me go back. 2 raised to the 4 minus 1, so that's a cubed. 2 cubed is 8. -5 times 8, so a sub 4 is -40. Okay, so the next question . So find the general formula of an arithmetic sequence. So we're given it's arithmetic, whose 8th term is 26 and whose 12th term is 42. So there's a couple different forms for an arithmetic sequence. One of them is in terms of a sub 1 and d, the common difference. A sub n, the nth term, could be defined as the first term, a sub 1, plus the quantity n minus 1, that quantity times d. So we're given two different information. We're given the 8th term. So this is when n is equal to 8. If we go back in here, and we know that that value, that term is 26. So let's find one equation. We know 26 is equal to the first term. We don't know that yet, a sub 1, plus, well, n is 8 on the 8th term. So 8 minus 1, so this would be plus 7d. We have a second equation that we can get for the 12th term, and this would be when n is 12. We know the 12th term is 42, so we have 42 is equal to the first term, which we don't know yet, plus n minus 1. Well, n is 12 here, so 12 minus 1, we would have 11d. So we have a system of equations. We have two equations, two unknowns. So let's use the addition method or elimination method. Let's sum in the negative. Let's do row 2 minus row 1. So 42 minus 26, that's going to give us, I believe, 16, is equal to a sub 1 minus a sub 1, those cancel, and 11d minus 7d is equal to 4d. So we're now have an equation with just d in there, and so we can divide both sides by 4, and we get that d then is equal to 16 divided by 4, which is 4. So knowing what d is, we're going to plug it back in here, but we also need to figure out what the first term a sub 1 is. And so we can plug that back into either one of these equations. I'm going to do it into the first one. The first one says we have 26 is equal to a sub 1 plus 7 times d, and d is 4. So we get 26 is equal to a sub 1. 7 times 4 is 28, so plus 28. Solve for a sub 1, subtract 28 on both sides. We get a sub 1 is 26 minus 28, which is -2. So with the given information, we're going to go back in, and we're going to plug in a sub 1, and we're going to plug in d of this arithmetic sequence, and then we have the formula for the nth term, the general formula. So a sub n is equal to the first term, which we found to be -2, plus n minus 1 times d, and d we found to be 4. So I can leave it like this, if I had to expand this and look at other terms, or we could expand it, but if I was going to look at other terms, I would expand it. For now, I'm not going to. Okay, so our next question, find the fraction that is equivalent to 0.1818181818, where a repeats and 18 repeats infinitely. Okay, let's look at this. We can break this down to look like a series. .18, we can think of this as 10 over 100. If we looked at 0.0018, this is the same thing as 18, right? All over, I need 4 zeros, so 10,000. So we can keep on doing this. So that would get rid of this, that would get rid of these first two ones. And then if I look at 0.000018, this could be 18 all over, I need 1, 2, 3, 4, 5, 6 zeros. And so I can keep on doing that. And notice if I look at 0.18 plus this 0.0018 plus this 0.000018, I would be getting back this number. And I need to go on for this forever. I'm believing this is what I was getting at. So I noticed that my numerator is always equal to 18. We need to figure out what is going on with our denominator. Our denominator, notice this is 10. This is like 10 squared. This is 10 to the 4th. This is 10 to the 6th. So notice that our denominator, we can think of this as 10 raised to the 10 to the nth power. And so this is going to give us just the term, but we want the summation of k equals 1 to infinity of this a sub n. I'm wondering if we can rewrite this a little bit. So I'm actually not exactly sure if that's what they wanted, or if I wanted what I wrote this. So I will look back into this, but I don't want to take the time in class to do that. Okay, so next question. We have for the sequence 8, 6, 9 over 2, 27 over 8, answer the following question. Is this an arithmetic geometric sequence or neither? Explain how you came up with the answer. So we can either think about this and see if we can find some sort of pattern that's happening here, or in order for it to be an arithmetic sequence, basically we have a common difference, which means that for every term we took and we subtract the term right before it, we better get back that same constant, and we call that constant D for arithmetic. So we could start testing this. So if I took my term, a sub 2 minus a sub 1. Okay, so a sub 2 is 6 minus a sub 1, which is 8. This gives me back negative 2. So now let's look at a sub 3 minus a sub 2. And if this is arithmetic, we better get back negative 2. Okay, so a sub 3 is 9/2 minus 6. So let's get a common denominator there. So this is the same thing as 9/2 minus 12/2. 9 minus 12, that's negative 3. So this would be negative 3/2. So notice that when I took the difference of two terms right next to each other, we did not get back the same value. So it's not arithmetic. Okay, so now let's look at the definition of being a geometric sequence. So in order to be a geometric sequence, that says that if we took a term, a sub n, and divide it by the term right before it, we're always going to get the same constant r called the common ratio. And so we can do the exact same thing that we were doing up here. And so, I'm sorry, with arithmetic, except for with division. And so if we look at a sub 2 divided by a sub 1, this would be 6 divided by 8, which let's reduce that. That gets me 2 goes into both of these, so this would reduce to 3/4. I want to look at a sub 3 divided by a sub 2. I'm running out of room.
Meeting is being recorded.
Okay, so looking at a sub 2 divided, or a sub 3 divided by a sub 1, and I was seeing if I could get some more space in here. That was the whole point of me. How do you do that? You don't have a, there we go. There we go, yay. Okay, so now let's look at a sub 3 divided by a sub 2. So a sub 3 value was 9/2. So we have 9/2 divided by 6. So this is equal to 9/2 times the reciprocal of 6, which is 1/6. We can reduce, 9 and 6 both have a 3 in common. So that goes in 3 times, it goes in here twice. And so if we go across, we get 3 all over 2 times 2, which is 4. Okay, so far we're good. These are the same, but let's do it for the next term too, because it's possible that it happens for a couple of them, but not all the time. So let's look at the next term in the sequence. So let's look at a sub 4 divided by a sub 3. So our a sub 4 term, that's a 27/8 divided by our a sub 3 term, which is our 9/2. Rewrite it. So this is 27/8 times the reciprocal of 9/2, which is 2/9. So simplifying, 2 goes into 8 4 times. 9 and 27 both have 9 in common. 9 goes into itself once, and 9 goes into here 3 times. Did I do everything right? I'm just seeing that. Oops, no, I didn't do everything right. 2 goes into 8 4 times. There we go. So multiply straight across. 3 times 1 is 3. All over 4 times 1 is 4. And so notice, same. Constant. So we actually found out what R is. R is equal to that common ratio, which is 3/4. And so this is a geometric sequence. So then it asks, what is the formula for a sub n? Well, it's geometric, so we know a sub n then, and again, is in the form of a sub 1 all times r raised to the n minus 1 power. By going through what we just did, we figured out what r is. Our common ratio is 3/4. And if you go back and you look at your sequence, it gave us the sequence of the first 4 terms, or the first 4 terms of the sequence. So we know what our first term is, which is 8. So a sub 1, and our sequence is 8. So knowing these two things, we now know our formula for a sub n. So a sub n is equal to 8 all times 3/4 raised to the n minus 1 power. So the next piece is asking us to find what is the sum of the infinite series. So we're looking at the summation of our sequence 8 all times 3/4 raised to the n minus 1. Or we can put k if we want, or n. K equals 1, but this time we're going to infinity. So for an infinite sequence, geometric sequence, it either converges or diverges, and it depends on our value of r. If the absolute value of r is less than 1, it converges. And notice that 3/4 is less than 1, so our series is going to converge. So there was a formula for that. And I told you that I would give you guys that formula. Let me pull that up. I don't have that on offhand. I believe it's, I can sit here and guess, or I can just look it up. Okay, so this, let me give myself some more room again. Okay, so the formula for this convergence of an infinite geometric series says that if you have the summation from k equals 1 to infinity of a sub 1 times r to the n minus 1 power, this is equal to the first term all over 1 minus r. So our series, this is equal to our first term, which is 8, all over 1 minus r, and r is 3/4. So this is equal to 8 all over, so a 4/4 minus a 3/4, getting a common denominator down here, is a 1/4. So this is equal to 8 times the reciprocal, which is 4. So 8 times 4 is 32. So if we sum these values up, those infinite sums of that sequence or series is 32. Okay, so go on to the next one. Okay, so our next example is an application, and we're looking at, we have several logs are stored in a pile with 36 logs on the bottom layer, 35 on the second layer, 34 on the third layer, and so on. If the top layer has 1 log, how many logs are there in the pile? Okay, so this looks like we're doing a series because we're summing. And it looks like the number of logs in our pile could be written as a formula where we can find the nth term. And so we have 36, comma, the next one we have 35, comma, the next one we have 34, dot, 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 down to 1. So looking at this, I can tell that my first term is a sub 1, which is 36. And then notice that to get from term to term, we're subtracting 1. And so I can see that this is an arithmetic sequence. And I can tell that D is equal to -1. So then we know that A sub n is the first term, 36, plus n minus 1, all times D, which is -1. So to me, this is where it's easier if we simplify. So let's distribute our -1 inside that parentheses. We still have that 36, and this would give us -1 times n, which is -n, and -1 times -1, so +1. So A sub n is equal to 37 minus n. That's not the question. It wants us to know how many logs are there. So we have k equals 1. And we're going to what? So we're going to the last row. So last row is going to have only 1 log in it. And if we put in 1 log, let's figure out what n is there. So if I subtract 37, I get -36 equals -n. So I know that my n value, I have 36 rows. Just want to make sure. Of our a sub n term, which is 37 minus n. So this is an arithmetic sequence or series, and so there's a formula, and I again will give you this formula, but what the arithmetic series says, if you have some k equals 1 to n of, so that's geometric, so the right one. Of an arithmetic sequence, a sub n, this is equal to n over 2, all times a sub 1 plus a sub n. So for our series, our n value is 36. So we have 36 divided by 2, all times the first term. Well, our first term is the number of logs in our row, bottom row, which is 36, plus the last term. Well, the last term in our row is 1. So this gives us 36 divided by 2, which is 18, all times 36 plus 1, which is 37. So we have 18 times 37, which gives us 666 logs. Okay, extra credit. For some reason, I thought this had partial fraction decomposition in here, and there's not. So let me just see what this says. So a carpenter wishes to construct an elliptical table top from a sheet of plywood, 4 feet by 8 feet. He will trace out the ellipse using the thumb, tack, and string method. So that we kind of defined it by that focus. what length of string should he use, and how far apart should the tack be located if the ellipse. Okay, good problem. Not going to be on the final. And that will take me, it looks like a great problem. And I would love to go through that, but it would take me a little bit of time to work out all that detail. And I'd rather go over stuff that you guys should have. So it looks like that was the end of that exam. Let's see if we can pull up another one. So I wanted to go over partial fraction decomposition. We also haven't gone over a system of 3 equations, 3 unknowns, and using matrices to solve. Okay, so asymptotes, we can come back to this. Graphing logs. This actually kind of looks familiar. This might actually look identical to what you guys had on your last exam. I pulled some questions. And so here we go. Systems of equations using matrices. Okay, so we want to put this in the augmented matrix form. So that means what we want to do is we want to rewrite this without any of the variables in here. We're going to make sure that it's all lined up where all of our x terms are in a column, y terms, z terms are equals, and then our constant. And that's already set up like that. So now I'm going to just start writing out my matrix. And so we have 1, -1, 2, and then a 7. We have 3, 2, -1, and then -10. We have -1, 3, 1, and -2. Okay, so I'm just going to go back and I'm just rechecking, because if I had written this down wrong, then we'd have to start all over. So 1, -1, 2, 7, so that's correct. 3, 2, -1, -10, that's correct. -1, 3, 1, and -2. Okay, good. Matrices work column to column. Usually it's best if you get that 1 where you need it. We have that 1 in that top first row, first column. We're trying to get 1s in this main diagonal. Once that's done, or we have 1s in the main diagonal and 0s above and below where possible, then we have our solution. We're going to use that row in this column. We're going to use that 1 to get rid of the entries below. So we're just using this row to manipulate the rows below. And so we're going to look at -3 times row 1 plus my row 2 would get rid of this 3 down here. And so I'm going to recopy down my row 1 because I'm really not changing it. I'm just using it to change the other. So row 1 was 1, -1, 2, 7. My new row 2, so -3 row 1, so -3 times 1 is -3, plus row 2, plus 3 is 0. -3 times this -1 is +3, plus the 2 below it gives me 5. -3 times this 2 is -6. -6 plus the -1 below it is -7. -3 times 7, that's -21. -21 plus a -10 below it is -31. So now I need to get rid of this -1 in the third row, first column. Again, I'm going to use this 1 in the first row to do that. And so if I look at row 1 and adding it to row 3, we would get that 0 where we wanted it. So 1 minus 1 is 0. -1 plus 3, we're going to get a 2 here. 2 plus 1 is 3. And then 2 times 7 is 14. 14 minus 2 gives me 12. Okay, so we're done with our first column. Now we're moving to our second column to work with. We want a 1 here in the second row, second column. Unfortunately, if we divide through by 5, we have fractions, which gives me more room for error. I also see if I multiply this third row by a half, I still would have fractions. So I'm trying to manipulate this somehow so that this gets me a 1 here. I can't use my row 1 because then I would be getting a number where I got a 0, and I don't want that. I notice that if I look at multiplying my row 3 by -2, because this would give me -4 plus 5, that would give me a 1. So let's manipulate it doing it that way. So -2 row 3 plus row 2. So my row 1 is the same, 1, -1, 2, and 7. My row 3 is actually staying the same, so let's write that, 0, 2, 3, and 12. It's my row 2 I'm manipulating. -2 times 0, 0 plus 0 is 0. -2 times 2 is -4, plus 5 gives me my 1. -2 times 3 is -6. -6 plus this -7 is -13. -2 times 12, what is that? -24. -24 minus 31, that's -55. Okay, we manipulated it. We now have the 1 where we want it in that column, and now we're going to use that to get rid of the entries above and below. And so we're using row 2. So I'm going to rewrite row 2, but I'm going to change the other 2, so I'm going to leave them blank for now. So my row 2 is 0, 1, -13, -55. And so notice if we take this row 2 and we add it to row 1, we would get the 0 above where we wanted it. So we're going to look at row 2 plus row 1 to give me my new row 1. So 0 plus 1 is 1. 1 minus 1 is 0. -13 plus 2, that gives me -11. And -55 plus 7. Just don't want to get off on my math. So -48. So doing the same thing using row 2, but now we're going to multiply it by -2 to get rid of the 2 below. So we have -2 row 2 plus row 3. So -2 times 0 is 0 plus 0 is 0. -2 times 1 is -2 plus 2 is 0. -2 times -13, that's +26 plus 3 is 29. -2 times -55 gives us 110, and 110 plus 12 is 122. Now I'm hoping that that is divisible by 29. No. Okay, so I'm not sure if I did some math wrong or this was a nasty problem and I probably would have went back and fixed it. So let me go back and look at this and see if I can find any errors real quick. So I'm going to pause that while I do that.
I think I found it.
Did you, Trinity? Where is it
I
at?
think it's R1 plus R3. The 12, it should be 5 because you're adding 7 plus -2.
Okay.
Right.
Yep. There it is. So this is 5. So we're going to go back and we're going to change a couple of entries. So when we did that, then we had to use this row to get row 2. So -2 times 5, that's -10. And -10 minus 31, that would have been a -41 here. Let's change this to 5. Let's change these. Okay, what did I say? Let me go back. -2, that's -10 minus 31, that's -41. This would still be the 5. So everything else. So row 2 plus row 1, that's not going to change things. -2, okay, here we go. -2, that's -26, that's 26 plus 3. -2 times 41, Maybe that 7's off. Let me go back on that 7 in a second. -2 times -41, that is 82. 82 plus 5 is 87. Yep, and that's divisible. Let me just check on my 7 right up here. Row 2 plus row 1. So this would have been -41 plus 7 from above, which is -34 up here. Okay, so I think I'm back on track. And so again, we talked about how kind of important it is so that you put down what you were doing so you can go back if you haven't found an error and trace what you need to change. So we're almost there. We finished the second column, moving to the third column. We need a 1 down here in the third row, third column. So we can do that by multiplying 1/3 times row 3. Not 1/3, I'm sorry, 1/29. 29 goes into 87 3 times. So our new row 3 is going to be 0, 0, 1, comma 3. Not comma 3, a line in 3. I'm going to rewrite my row 1 and row 2. So row 1 was 1, 0, -11, and 7. Row 2 was 0, 1, -13, and -41. Okay, so now I'm using my third row to get rid of the entries above that 1. And so if I look at 11, row 1, row 3 plus row 1. So I'm going to rewrite my row 3 because that's not changing. So 0, 0, 1, 3. So here we go. We got 1 in the first row, 0. 11 times 1 is 11, minus 11 is 0. 11 times 3 is 33. 33 plus 7 is 40. Getting rid of the -13 here, we can do 13 row 3 plus row 2. So we get 0, 1, 0. 13 times 3 is 39. 39 minus 41 is -2. So if I did everything right, we get x is equal to 40, y is equal to -2, and z is equal to 3. I can test it by going back in and checking it has to work for all 3 equations. So is 40 plus 2, yeah, something's wrong. I'm going to go back and trace this number. Shoot. Row 2 plus row 3. Row 2 plus row 1. Now let me pause it while I'm finding the error. Okay, so the error had to do with this and copying it back over here. So -34 plus 7 is, -41 plus 7 is -34. So we have a -34 here. And so now when we look at getting rid of the -11 here using row 3, that would have been 11 times 3, which is 33. 33 minus 34 is -1. So that should be a -1. And then now let's go back and test to make sure that we did this right. And so -1 is our x value minus y. So minus -2 is +2. Plus 2 times z, 2 times 3 is 6. Does this equal 7? And it does. So first equation works. Plugging in the second equation. So 3 times -1 is -3. Oops, shoot. And so we got -3. -2 times 2, so that's -4. Z, so -3. Is this equal to -10? And it is. Last equation, we get negative of -1 is 1. 3 times y, 3 times -2 is -6. 1 times z, so that's 3, plus 3. Is this equal to -2? 1 minus 6 is -4, no, 1 minus 6 is -5, -5 plus 3 is -2. Yay. Okay, so we found the solution. Thank you for your help in recognizing where my error was. Okay, so I know that these can be tricky, and if you get off, then going back and finding it. So if that happens to you while you're on the exam, you could always come back to it. You can always state, I know this is what I need to be doing, and but something's going wrong and it's not coming out. So I know that you have some idea and you know what to do, and then I can give you some partial credit. Okay, so the next question is great. So while using a matrices to solve a system of equations, you come up with the following matrix. What does this mean? Why? If the system has solution, write an ordered point such that you can find the points that satisfies the system. If you rewrite this matrix in terms of a system of equations, let's call this first column our x. These are coefficients of our x terms. This is coefficients of our y terms, z terms equals. So our first row would represent x. Let me put this back on. It would represent x plus 0y plus 0z equals 4. The second equation, we would get 0x plus y plus 4z equals 8. And here we have 0x plus 0y plus 0z equals 0. If this had no solutions, then we would have gotten a number over here other than 0. And we would know that that's false because you can't multiply something by 0 and get a number other than 0 back. Sorry, it keeps jumping. So we look at our first equation here. This is saying that x is equal to 4. Here, this is saying that y plus 4z is equal to 8. So let's just rewrite y in terms of z, or we could rewrite z in terms of y, but it looks like it's easier to rewrite y in terms of z. So we have y is equal to 8 minus 4z. So our point or a solution, x will always be 4 for the solution. Our y value depends on what z is. Our y value is going to be 8 minus 4z. And our z value is just z. Get this right, an ordered pair such that it would find points that satisfy. So this would be our ordered pair that would satisfy our system. Okay, so partial fraction decomposition. I'll give myself more room. Just gonna make a new page, makes it easier. Okay, so to determine the partial fraction decomposition of the following. So we have 6x squared minus x plus 3 in our numerator. We have x cubed minus x squared plus x minus 1 in our denominator. First thing that you want to look at is the degree of our denominator smaller than or equal to the degree of our numerator? If so, we have to use long division. So looking at it, it's not, so we're good there. The next step is we want to factor the denominator as far as possible in terms of factors of linear, product of linear factors, and or quadratic being irreducible over the real numbers. And so looking at the denominator here, I notice I have 4 terms, nothing uncommon, but 4 terms. When I see that, flags me in that I should probably try factoring by grouping. If that didn't work, then I can use some of my tools we learned in this class and look at that P over Q and start testing numbers to find the zeros, and then we would be able to factor. Okay, so looking at this, this is the same thing as 6x squared minus x plus 3. Actually, maybe above, I'll do that factoring by grouping. So if I pull out an x squared, actually I can do it here. That would give me x minus 1. Well, notice x minus 1 doesn't have anything in common, but I'm just going to put a parentheses around there, and I can pull out the x minus 1. If I pull out an x minus 1 from here, I'm left with x squared plus 1. So I can rewrite this, my denominator factored as x minus 1 all times x squared plus 1. X squared plus 1 is not factorable over the real numbers. They have quadratic roots. So once you've factored this completely, depending on what type of factor you have, and is it repeating, depends on how you're going to rewrite this. And so I have x minus 1. This is not a repeating factor, so I'm going to rewrite this as a all over my x minus 1. If this had been repeating, I would have to have, so let's say this was cubed, then I would have to have 3 fractions representing this x minus 1 quantity cubed. I'd have a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed, and I would do that until I got to that power. The next type of factor, x squared plus 1, is quadratic, again, irreducible over the real numbers. And so when we rewrite quadratic factors, the numerator is going to be in the form of bx plus c in this case, all over x squared plus 1. Again, if this was a repeating factor, I would continue to go on in that number of factors until I got to this power that it was. Okay, so once you've rewritten it, now we can multiply through by our LCD. And if we multiply through by our LCD, we would be left with our numerator on the left-hand side, which is this 6x squared minus x plus 3 is equal to, well, multiplying by the LCD, we would have our a in the numerator times the piece that was missing. Our x minus 1's cancel, you're left with the x squared plus 1. Plus, so we're going to have our numerator here, bx plus c. And when we multiply through by the LCD, the x squared plus 1 cancels, and you're left with a factor x minus 1. This is the one we can't use that shortcut I was telling you about, so we want to expand this, and so let's just rewrite it. We have 6x squared minus x plus 3 6x squared minus x plus 3 equals, distributing my a, I get ax squared plus a plus, we need to distribute, so bx times x, so bx squared, bx times -1, so minus bx. Distribute your c, so c times x, so plus cx. C times -1, so minus c. So when we were doing this, I want sorry guys. Go away. Okay, so when we're doing this, we want to look at our coefficient in front of the x squared. So our 6x squared, well, when we look at all of our terms and sum them over here, the ax squared plus the bx squared, well, this a plus b would have to sum to give us 6. So we know 6 then is equal to a plus b. You don't have to worry about the variable piece. And now let's look at the coefficients in front of our x term. So our x variable here, our coefficient is -1. This is equal to, well, negative bx plus cx has to equal -1. So negative b plus c. And then let's look at our constant. And so our constant is negative c. And a. Our constant over here is 3. So notice that 3 is equal to a minus c. Okay, so we have a system. We have 3 equations and 3 unknowns. So let's do this using matrices. So I might have it on there, so that would work for two things. One question showing me you know how to do 2 things. And so let's look at the first equation. So this would be our first row would be 1, 1. There's no c value, 0, and then it's equal to 6. Our second row, we don't have an a value, so 0, -1, 1, and then it's equal to -1. Our third row is 1, we don't have a b value, 0, -1, and 3. So let's look at negative row 1 plus row 3 to get rid of this 1 down here. I'm going to rewrite row 1 and row 2 because we're not changing them right now. So -1 plus 1 is 0. -1 plus 0 is -1. -1 times 0 is 0, minus 1 is -1. -6 plus 3 is -3. So now let's look at negative row 2. So that's going to change my signs in here. That would make this a positive 1. This is going to make this a -1, and this is going to make this a positive 1. So now we can use this 1 to get rid of the entries above and below. So let's look at row 2 plus row 3. So I'm going to rewrite row 2 because that's the one I'm not changing. 0, 1, negative 1, and 1. And 0 plus 0 is 0. 1 minus 1 is 0. Negative 1 minus 1 is negative 2. And 1 plus 3. Is that negative 3 or 3? Negative row 1 plus. That's a negative 3. Row 1 minus 3, so that's negative 2.
For row 2 plus row 3, the 1 at the end, is that supposed to be negative or positive?
Right here?
Yeah.
Okay, so let me do it again. Hold on. I get so confused. Okay, I'm using this row to change this. Yeah, it would be negative. And now what am I doing? My whole goal right now is working with this. So I'm looking at negative row 2 plus row 1. So that gives me 1. Negative 1 plus 1 is 0. Negative times negative 1 is positive 1. 1 plus 0 is 1. And then I'm doing negative of this. It's negative 1 plus 6 is 5. So if we multiply negative 1/2 times row 3, that would change this to 0, 0, 1, 1. So I'm going to look at this row, so negative row 3 plus row 1. Let me just rewrite row 3. So that was, and our new row 3 after multiplying through by half was 0, 0, 1, and 1. So negative row 3 plus row 1. So 0 plus 1 is 1. 0 plus 0 is 0. 1, negative 1 plus 1 is 0. Negative 1 plus 5 is 4. Now we want to get rid of this negative 1. And so we're doing row 3 plus row 2. So 0 plus 0 is 0. 0 plus 1 is 1. 1 minus 1 is 0. And 1 plus 1 is 2. So this tells me my A value is equal to 4. My B value is equal to 2. And my C value is equal to 1. So back up here, plugging in our values, our thing is A, which is 1, all over, A, which is 4, all over x minus 1, plus B, which is 2 times x, plus C, so plus 1, all over x squared plus 1. This is the same thing as our rational function we started with. Okay. So I think we went over, and we can look at those questions later if you want. I think we went over the material from the last exam that we covered since the last exam. So we covered the conic sections, ellipses, parabolas, hyperbolas, circles, looked at given information, being able to find the equation, or given the equation, putting it in a form so that we could graph it and tell information about it. We looked at sequences in series. We looked at an arithmetic and geometric sequences in series. We looked at systems of equations. We looked at systems of nonlinear equations and graphing. Looked at matrices, and we just looked at fraction decomposition, partial fraction decomposition. And if I'm not mistaken, I think that is everything since that last exam. So let's take a break, and then we'll come back and we can go over stuff that was covered on the first 2 exams, because it's possible some of that information is on the test too. Let me pause the video. Okay, so we're continuing to review for the final, and let's go over the difference quotient. So you should be able to look at the difference quotient. So the difference quotient, recall, this was f of x plus h, all minus f of x, all over h. So if you were given, let's say, f of x is equal to 1 over x, apply the difference quotient to that. So if we're looking at f of x plus h, that's telling me I'm going in to my equation f of x, and I'm plugging in x plus h wherever I see an x. And so I would get 1 over x plus h here, then minus f of x, so minus f of x is 1 over x, all over, and then h. So you want to simplify this. This is a complex fraction. We want to get rid of the complex fraction. A couple ways we can do that. One way is we can multiply by this fancy 1. The 1 is the least common denominator of the fractions within. You can think of this as over 1 if you want. And so our LCD would be x times x plus h. So we're multiplying this by 1. We're going to distribute it into our numerator. And once we do that, our denominators are going to go away. So when we distribute, our x plus h cancels, leaving you with just an x minus. Distributing here, our x cancels, and we're left with the quantity x plus h. All over, so distributing down in the denominator, nothing cancels, and you're left with h times x, all times x plus h. I'm not going to distribute on the denominator. I'm going to leave it in that factored form, but in the numerator, let's simplify. So let's multiply through by a -1. And so we have x minus x minus h. So x minus x cancels. We are left with a -h in the numerator, all over h times x plus h. And notice your h's cancel. We can do that because this is strictly multiplication down here. And so you're left with a -1 all over x times x plus h. So you should be able to do the difference quotient. You should be able to look at a graph. You should be able to tell where it's increasing, where it's decreasing, where it's constant. You should be able to find the domain, the range of a graph. So let's say you had a piecewise function. F of x is equal to, how about the absolute value of x minus 1 if x is between, let's say if x is less than 3. And let's say you had 2x minus 4. If x is bigger than or equal to 3, but smaller than I don't know, 6. And let's say x is equal to -5 if x is greater than or equal to 6. So let's look at the graph of the following. Okay, I just want to make sure I had started the recording, and I had. So graph the following. So let's look at the piece x minus 1, that absolute value. And so we can think about that using transformations of a graph. The absolute value of x minus 1, this would be a transformation of the graph, the absolute value of x, which is a v, where that point is at the origin. This minus 1 is shifting it over 1 unit to the right. And so we have this graph like here that looks like a V. But we need to stop when x equals 3. And so x is equal to 3. If we plug this in, we can figure out what y is. So the absolute value of 3 minus 1, 3 minus 1 is 2. Absolute value of 2 is 2. I don't know why. Anyways, so at that we have 2. But it's an open circle because it's not included on that piece of the graph. So now you want to graph the piece here where x is between 3 and 6. So when x is 3, let's plug in 3 for x. So when x is 3, we get 2 times 3 is 6. 6 minus 4, that is 2. So I'm going to actually color this in because there's actually a point there. And then let's see what's happening at x equals 6. So if we plug in 6 in for x here, we get 2 times 6 is 12. 12 minus 4 is 8. So at 6, we get 8. I know that this 2x minus 4, it's a line. So there's not going to be any curvature in there. Whoops. Except when I do it on my, on my tablet. And then we want to graph the other piece. And this is going to stop here. And this was a solid. Oh, no, it's not solid. It's less than 6. So this has to be an open circle at 6, 8. So now we want to graph the piece x equals -5. And this is for x is greater than or equal to 6. So this is a horizontal line at -5. And it's a solid circle at 6, -5. Any value we plug in for x bigger than 6, y will always be -5, so it continues on this way. So you should be able to answer questions about the graph. So the domain, what's the domain of f of x? Well, on a piecewise function, it's pretty much told by the pieces of the inequality. It says that x is smaller than 3. X is between and including 3 and 6. Not including 6, but it includes 6 here. So our domain, we're hitting all of our x values. There's nothing that we would exclude. So the domain of f of x is -infinity to infinity. If we wanted to find the range, well, looking at our graph, we can now tell what our range is. So notice ranges of the y values. Notice that we're hitting a y value of -5, but we don't hit any y value that is below -5. And so one piece, we have a y value that's -5, union. Well, I don't have any y values between my graph of -5 and 0. I do have a point when y is 0, so I'm going to start at 0. I'm going to include it, so I'm going to put that bracket there, comma, and then I'm looking at all the other y values I'm hitting on my graph. Well, this piece here stops at y equals 8, but my piece for the absolute value of x minus 1, that's for x's less than 3. This is going to continue on forever. It's going up, shooting upwards as x goes to -infinity. So I'm hitting all my positive y values. So I'm going from including 0 to infinity. You should be able to tell, again, intervals where it's increasing, decreasing, and constant. So increasing, this is where our graph is going up from left to right. So if I'm following my graph, I'm actually coming down, I'm decreasing in here until I hit 1. And then once I hit x equals 1, I start to increase. When we're looking at where it's increasing and decreasing, we look at the x values. Those are the values that you're saying. So it's starting at 1, excuse me, and it's stopping at 6. So it's increasing between x equals 1 and 6. So this is not a point. Another way to state this is 1 is less than x is less than 6. And so now we're going to look at where is it decreasing. So looking at the graph, reading it from left to right, you're looking at where it's going down. It's going down here, but we're only looking at the y value, or I'm sorry, the x values. So we're looking at all the values coming in from -infinity until we hit 1. And so it's decreasing from -infinity to 1. Or x is less than 1. And then it's constant. That's where the graph is horizontal. It's when your y value is always the same. Your y value is always the same from x equals 6 to infinity. Another way to state that is x is greater than 6, or greater than or equal to. You should be able to answer questions about the graph, find f of some value. So if it said find f of 3, you should know that which equation that you would be using. It depends on which interval it falls in. Well, x equals 3, this it falls in when it's 3 is less than or equal to x is less than 6. So this would tell me that I'm using my second equation for this. And so this would be 2 times 3 minus 4, which is 6 minus 4, which is equal to 2. What else? You should be able to find when, let's say, find when f of x is greater than or equal to 2. So this is asking, when is my graph hitting y values that are greater than or equal to 2? Well, if we look at our graph, which we graphed, and we look at x equal, or y equals 2, let's just put a horizontal line there. So we're looking at, when is this graph going above, when are our y values bigger than or equal to 2? And so you can see that it's happening here, and everything less than that Need to figure out what that X value is though. And it's also hitting here, where that first was an open circle, but then the other piece actually filled it in. And so it's hitting here. I can see it's from 3, oops, and it stops at 6. After that, we're falling below the x-axis, and -5 is smaller than 2. So I know I have 3 to 6. Not including 6, union. So I need to figure out this value here for x. Well, let's determine what equation, what piece of the equation we're using. Well, that was absolute value of x minus 1. So we're looking at the absolute value of x minus 1. When is that equal to 2? When is that absolute value of x minus 1 equal to 2? Absolute value equations we solve a little differently. We first isolate the absolute value, and then once we've isolated the absolute value, we rewrite it as 2 separate equations. We write what's inside the absolute value equal to the other side, 2, and we look at x minus 1 equal to the negative of the other side, -2. And then we solve for them there. So if we look at this, this is x equals 3. And if we look at here, this was x1, x is equal to, adding 1 to -2, we get -1. So this value here is when x is -1. So anything smaller than or equal to -1 would give us a y value bigger than or equal to 2. Here it says x equals 3. Well, this was actually part of it. It was an open circle because it wasn't included, but again, it had hit it. This could have fallen out of my domain for that piece, and then I would have just ignored it. But right here, I'm just worried more about the -1. That's what I was looking for. And so it's also bigger than or equal to, f of x is bigger than or equal to 2 when x is coming from -infinity and then -1, and we're going to include it because the equal to part is there. You should be able to look at your graph and determine if there's any absolute max or absolute mins or local max, local mins. We have a local min. Notice in the local min, we talk about the y value. So we have a local min here at y value is 0. So we have a local min of 0. And then we say the x value tells us where it is at x equals 1. Okay, so I notice that we have a local min when of 0 at x equals 1. Okay, so notice here we have some interval where this value that's where I'm a little, I need to check to see if we would include this. I believe we do. And we have a local max of 6 at x equals, oh, that was a max of 8 at x equals 6. Okay, but I would have to double check to make sure that that information is correct. If I can do that when it's an open circle, I would have to go back right now and look at the definition of absolute max and absolute min to see if that fell in the parameters of what has to hold. Okay, but don't worry about that in the fact that if you had something like that, it would be obvious that it was a local max or local min. Solving exponential equations are really important. Solving log equations are really important. Being able to rewrite logs. It's really important to be able to rewrite something that's really a nasty log into something that's simpler. That's going to be helpful in calculus. Being able to recognize and solving all different types of equations is really, really important. And we went through when we solved, it was kind of a review, but a little more extensive than intermediate algebra, but we went through and we solved all different types of equations, finding zeros of a polynomial, rewriting a polynomial in terms of linear factors and or quadratic factors. What else? Gosh, we went through so much material in this class. Graphing rational equations, graphing conic sections, graphing logs, graphing exponentials, using transformations of graphs. It's possible you might have a sheet of equations and a sheet of graphs where you have to match those equations to the graphs, where you might have more graphs than the equations. So just being able to look at it maybe and determine, okay, well, that's in standard form and that's in standard form of an ellipse, and I can see that, you know, my center is here and it has to be elongated here. And so it should be where it comes out pretty fast that you can identify. Trying to think of other things. So those are, we're all kind of discussing what you should be able to do, but we didn't go over any of those types of problems. So any of those things you guys want to go over and look at? Okay, so I thought that you should really need to know how to graph rational functions. That's going to be helpful in calculus, being able to figure out where your asymptotes are, knowing that a graph doesn't cross a vertical asymptote. It can cross a horizontal or a slant, but knowing about horizontal asymptotes and knowing the effects of the graphs, what's happening to your function as x is going to infinity or negative infinity. So we decided to review graphing a rational function. And so let's look at one. So let's say f of x is equal to, and I'm just grabbing one up in thin air, x squared minus 4 all over x squared minus x plus 6. Okay, so let's look at this. Let's see if they have any vertical asymptotes. So vertical asymptotes occur where our function, the denominator, is equal to 0, values that make that equal to 0, but not also our numerator. And so let's rewrite this. This is x squared minus 4. This is in the form of x minus 4, x minus 2, all times x plus 2, divided by x squared minus x plus 6. Oops, let me see. I wanted this to be, let's rewrite this to the minus 6. Change that. Okay, so the two numbers that multiply this to a negative 6 and add to negative 1, so negative 3 and positive 2. So x minus 3 and x plus 2. Okay, so again, vertical asymptotes occur at values that set our denominator 0, but not also our numerator. And so x equals 3 is a vertical asymptote. But x plus 2, or x equals negative 2, sets this 0, but it also sets our numerator. So x cannot be negative 2, and there's going to be a hole in the graph when x equals negative 2. So we can figure out where that hole would be is if we had simplified and canceled out these like factors, and we go back in now and we plug in negative 2 wherever we saw an x here, Well, -2 minus 2, so my y value would be -2 minus 2, -4, all over -2 minus 3. Well, that's -5, so that would be at 4/5. So there's a hole again at -2 is the x value, the y value though is 4/5. Horizontal asymptotes, those occur and we have to look at the degree of the numerator and the degree of the denominator, and we verify if it has one by looking at that. If the degrees are the same, then you look at the leading coefficient on the top, which is 1, and the leading coefficient on the bottom, which is 1. So we have a horizontal asymptote at y is equal to 1. If it has a horizontal, it doesn't have a slant. And so now the other things that would be helpful are finding your intercepts to help us graph. So let's find our x-intercept and y-intercept. X-intercept is when our y value equals 0. So we have 0 is equal to, we can look at this version that we simplified, x minus 2 all over x minus 3. Well, if we multiply both sides by our denominator, you're only worried about when is our numerator equal to 0. So we're looking at when is x minus 2 equal to 0, and that's when x is 2. Okay, so we have an x-intercept at 2, and that's the point at 2, 0. Our y-intercept occurs when x equals 0. So if we look at f of 0, we plug in 0 wherever we see an x, we get -4 all over 0 minus 0 over -6. This reduces, and two negatives make a positive when division, and so 2 goes into 4 twice, 2 goes into 6 3 times, so that reduces to 2/3. So we have a point at 0, 2/3 for our y-intercept. So let's start putting our pieces together. So we have a horizontal asymptote, we said at y equals 1. So I'm going to denote it by a dotted line. We said we had a vertical asymptote at x equals 3. We ended up having a hole in the graph when x was -2. Y was 4/5. So while 5 goes into 4, well, it doesn't, but 5 goes into 48 times, and so that's a 0.8. And so 0.8 is about here. I'm just going to estimate. And then our intercepts, we had an x-intercept at 2, 0. And we had a y-intercept at 0, 2/3. Well, 3 doesn't go into 2, but 20, it goes in 6 times. And then it's going to be repeating, so 0.66666, which is here. And so what we need to do is plot a couple points, if it's not already done, to figure out what's going on, and you do that on each side of a vertical asymptote. We only have one vertical asymptote. We have multiple points on this side of the left-hand side of our vertical asymptote, so you should be able to see what's going on with the graph. So we don't have any points on the other side of x equals 3. And so we need a test, but I know pretty much that I'm not crossing my axis again, my x-axis, and I have this vertical asymptote, so my guess is that it's going to be this shape above here like this. But let's just test a point. So a point to the right of x equals 3, so how about 4? And let's go back in, and we want to plug it back into our equation. And so f of 4, just pull up that equation. Okay, so looking at f of 4, 4 squared is 16 minus 4 all over 4 squared is 16 minus 4 minus 6. So 16 minus 4 is 12 all over 16 minus 4, which is 12, minus 6 is 6. So this would be 2. So we know I have a point at 4, 2. So going over here, going to 4 and up 2. So it's just like I said, I think it's going to be above here. And so I can tell with where the asymptotes are that it looks like this. So I may ask you, does the graph cross an asymptote? So just like I stated before, it can't cross a vertical asymptote ever, and that's because it's undefined there. It is possible, though, that it crosses a horizontal or slant asymptote. So we want to know, does our function f of x, would it ever equal the y value of 1? Because that's our horizontal asymptote. And so we want to know, is 1 ever equal to x squared minus 4 all over x squared minus x minus 6? So it's an equation, we can clear our fraction. So let's multiply both sides by our LCD. So multiplying both sides by x squared minus x minus 6, we get x squared minus x minus 6 is equal to, well, that canceled, just our numerator, x squared minus 4. We want to get all of our x's to one side, or actually it's quadratic, so that's the first thing I would think. Okay, let's get all the x's to one side, or everything to one side. But when I subtract x squared, notice our x squared term cancels, and we're left with negative x minus 6 equals negative 4. So to me, this is telling me then this is now a linear equation. I solved this differently. So let's add 6 to both sides, get the x by itself. We get negative x equals negative 4 plus 6 is 2. And then multiply both sides by negative 1 or divide by negative 1, we get x equals negative 2. Okay, x equals negative 2. This is undefined for f of x. That sets our denominator equals 0. And that should have been one of our stipulations up here, and that could be a good question, is what is the domain? And so our domain are all values except for 3 and negative 2. A couple of ways we can write that. Interval notation, negative infinity to negative 2, not including parentheses, union. Don't forget the numbers in between those. Some of you guys did that on the test. So negative 2 and 3, union, and then 3 to infinity, not including the negative 2 or 3. What about the range? So we all should be able to, after graphing something, be able to tell about the range. And so when looking at the range, well, we just solved to see, would this graph ever cross y equals 1? And we saw that it couldn't because we was undefined there. And so we know we're never going to have a y value of 1. What about over here? There's this y value right here. That's an open circle. This piece of the graph over here, it's above this. It's never going to hit that y value. So I notice that there's 2 y values in my graph that's never going to hit. So the range is going to be all reals except y can't equal 1 and y cannot equal, well, that whole was at negative 2/4. Okay, so end behavior wise, if we were looking at this, and I wanted to look at what's going on with our graph as x is going to negative infinity. Well, as x is going to negative infinity, what is it going to? What is your y value going to? Well, this is getting closer and closer. It's getting closer and closer to 1, so it's going to 1. So our end behaviors, we can look at our graph and be able to tell. So as x is going to positive infinity, wanting to look at our graph, as x is going to positive infinity, notice our y value is getting closer and closer to 1. And so our limit as x goes to infinity is 1. Again, we can talk about increasing and decreasing. Notice this is strictly decreasing here, and then it's decreasing here. We just can't include a couple points, 3 and negative 2. Okay, trying to tie in a lot of different things into a couple questions. Okay, trying to think now of other things to go through. So like I said, being able to solve all different types of equations are really important. So linear, quadratic, absolute value, rational, ones with radicals, exponential, logs. So while you're doing that, you should also be aware there's some times where you have to be careful because of the value that you get in your answer is not part of your domain, and you have to exclude it and it won't work. And so you need to be aware of those things. You should be able to do, like we talked about, the systems of equations. But not only of these did we solve, we also did inequalities. So you should be able to solve these with inequalities. I'm just trying to brainstorm. So maybe let's go through finding zeros of a polynomial. So let me just pull a question. I can't just come up with one of those in my head. Oh, while I'm thinking about it, you should be able to find inverse functions. You should be able to say, does a function have an inverse? If it does, you should be able to find the inverse. You should know properties of a function and its inverse. You should be able to take composition of two functions. So that was that little f of g of x, or the same thing as f parentheses g of x. So you're plugging in the equation of g of x wherever you see an x in f of x. You should be able to find the domain of composition functions. So this was where it was a little trickier. You had to be careful first, because first when you're plugging in values for x, you're plugging it into the inner function g of x. So first you had to worry about what is the domain of g of x. We had to exclude anything that gave us trouble spots. Then we had to look at the domain of f of x. But the thing is, with the domain of f of x, it was the y values we were going to be getting back from g of x that we were plugging in here. And so once we found the values that made it undefined for f of x, we had to set g of x equal to that and figure out what the x values were and exclude those. Okay. That came to mind while I was looking for a problem for finding zeros. Let me say it before I forgot. Okay, solve the equation in the real number system. And we have the equation 2x to the fourth plus 2x cubed minus 11x squared plus x minus 6 equals 0. Okay, so looking at this, I would first see if I could factor it, and there's no way I can factor this. And so at least write offhand by using methods from before. So let's just not think about this as an equation for a minute, and let's look at f of x, maybe f of x equal this 2x to the fourth plus 2x cubed minus 11x squared plus x minus 6. And so let's use some tools that we learned this class period. And so let's look at our possible rational zeros, because technically when we're solving this equation, we're looking at when is this equation equal to 0, what values. And so I'm going to look at our possible rational zero theorem, or rational zero theorem. And we're looking at our p-values. Those are factors of our constant, so plus or minus. Numbers that go into 6 evenly are 1, 2, 3, and 6. And divided by my q value, q are factors of my leading coefficient, or my leading term, which is 1 and 2. So when I look at p divided by q, and I don't have to list numbers twice, If I look at 1 divided by 1, I get 1, so plus or minus. 1 divided by 2, I get 1/2. And now I'm done. Now let's go here. So 2 divided by 1 is 2. 2 divided by 2, well, that's 1. I already have that listed. So now let's go to 3. 3 divided by 1 is 3. And 3 divided by 2 is 3/2. Going to the next number, P, 6. 6 divided by 1 is 6. And 6 divided by 2 is 3. So if this function has a rational 0, it would be one of these numbers. And so then we looked at using synthetic division to help find those zeros. So if I look at 1 here, let's put the leading, put the coefficients in descending order of powers down, and there's no missing powers, so we're good. We don't have to put a 0 as a placeholder. So we have 2, 2, negative 11, 1, negative 6. Bring the 2 down. 1 times 2 is 2. 2 plus 2 is 4. 1 times 4 is 4. Negative 6 plus 4 is 7. 1 times 7 is 7. 1 plus 7 is 7. 1 times 7 is 7. Oops, wait. 1 plus 7 is not 7. It's 8. 1 times 8 is 8. Negative 6 plus 8 is 2. Okay, so that one doesn't work because I didn't get a 0 here. If you remember upper bound, lower bound theorem, if we were testing a positive number and our whole row when doing synthetic division was positive, that told me there was no number greater than that, that could be a 0. So that actually excludes some of these numbers I have to test if I remember that theorem. So I'm not going to test any more positive numbers. I'm going to now go to my negative numbers. So let's look at negative 1. So again, let's rewrite this. 2, 2, negative 11, 1, negative 6. Let's bring down 2. Negative 1 times 2 is negative 2. 2 minus 2 is 0. 0 times anything is 0. Negative 11 plus 0 is negative 11. Negative 1 times negative 11 is 11. 1 plus 11 is 12, and this is not going to work. That is negative 1 times 12 is negative 12. This is negative 18. Does this alternate in signs? And it doesn't on the bottom, so we're okay. Let's start again. It could be negative 1/2. It could be, let's look at negative 2. So 2, 2, negative 11, 1, negative 6. Bring down 2. Negative 2 times 2 is negative 4. 2 minus 4 is negative 2. Negative 2 times negative 2 is positive 4. Negative 11 plus 4, that is negative 7. Negative 2 times negative 7 is 14. That's not going to work. 15. 14 plus 1 is 15. This is negative 30. This is negative 36. Let's try negative 3. Might have done something wrong back up here, but let's try negative 3. Just making sure I wrote everything down right. Okay, so let's try negative 3. So 2, 2, negative 11, 1, negative 6. So let's bring down the 2. Negative 3 times 2 is negative 6. 2 minus 6 is negative 4. Negative 3 times negative 4 is 12. Negative 11 plus 12 is 1. Negative 3 times 1 is negative 3. 1 minus 3 is negative 2. Negative 3 times negative 2 is 6. And we get 0. Yay! So we know x equals negative 3 is a 0. We know that x plus 3 is a factor. We also know this bottom row, so let's decrease it. Our original f of x, that was a fourth power, so this is a cubic. This is 2x cubed minus 4x squared plus x minus 2. I notice here I can do a factoring by grouping. Let me go back and pull our original equation. Well, our original equation, we were looking at when was this f of x equal to 0. So if we can get this in factored form, and so let's factor by grouping here. And so notice our first two terms in that second parentheses both have a 2x squared in common. We pull out a 2x squared, you're going to be left with a x minus 2 plus, notice right here, you're left with a x minus 2. Is equal to 0. So we have x plus 3 all times, well, let's factor out that x minus 2 piece. If you pull out x minus 2 from this piece, you're left with 2x squared. If we pull out x minus 2 from this piece, we're left with plus 1. So we're looking at finding the zeros of this polynomial. And so the zeros are x equals -3, x equals 2, and also when 2x squared plus 1 equals 0. So let's, even though it's complex or an imaginary number, let's do it anyways. So we have 2x squared equals -1, divide both sides by 2. So we're looking at x squared equals -1/2. When we take the square root of both sides, we get x is equal to plus or minus the square root of -1/2. So plus or minus the square root of -1 is I, all over the square root of 2. You should get good at rationalizing denominators, so let's do it. Multiply both top and bottom by root 2. So we get x is equal to plus or minus root 2i, or I root 2, all over square root of 2 times square root of 2, square root of 4, which is 2. Okay, so we have 4 complex zeros. Oops. I want to go back up here because I stated that I couldn't have another number larger than 1 as a 0, and so I know that I did something wrong up here. So I just kind of want to go back, and I see it right here. So here, that would have burned down my 2. 1 times 2 is 2. 2 plus 2 is 4. 1 times 4 is 4. Right here, -11 plus 4 is -7. And so that upper bound theorem would not have held here. And then I would have gone and tested 2. And I would have seen right away that that had worked. So we applied something that we learned and found zeros of that polynomial from this course, but we wouldn't have been able to do that without knowing or using that rational zero theorem. You should be able to rewrite it like we did. So some of you guys got that off. Rewriting a polynomial in terms of linear and or quadratic polynomials. So right here, we did all the work. So our graph, or f of x, is equal to x plus 3, x minus 2, 2x squared plus 1. We even went further on that last exam where I said, okay, go even further and rewrite it as linear, all of it linear factors, even if the factor had imaginary numbers in there. And so we can think of it using it this way. Actually, Yeah. Let's multiply both sides. So let's look at it this way. So x equals I root 2 over 2. So let's get this to 0. Usually you don't have fractions when we have it over here. So let's first multiply both sides by 2. So we get 2x equals I root 2. And then if we subtract I root 2 on both sides, we get 2x minus I root 2 equals 0. So that would be one of the linear factors of 2x squared plus 1. So that we said was 2x minus I root 2. And the other one was x equals negative I root 2 over 2. We multiply both sides by 2. We get 2x equals negative I root 2. Add both sides, I root 2, just set it equal to 0. We get 2x plus I root 2 equals 0. So that factor would be 2x plus I root 2. So here is that function f of x in terms of a product of all linear factors. We looked at in this class transformations of functions. So you should be able to look at and figure out what is I called the parent function. What is a function that we can manipulate that using those transformations on that function. So you should be able to do graphs, transformations. So horizontal shift, vertical shift, reflections. So reflections of graphs. Across x and y axis. Even and odd functions. Which kind of ties into symmetry, which is where we're talking about the reflections, so symmetry. We talked about symmetry with parabolas, so we already talked about conic sections, so we don't have to go there. I can't think of anything else that you guys have covered. Complex numbers, but kind of talked about that when we were doing this over here. So I think that's it. So let me stop for now. So this is the end of the semester and we'll take the final tomorrow, but let me touch base with you guys before I let you go for the day.